I hold in my hands what is theoretically a very simple apparatus. There's a valve in the middle that can control flow open or closed. I have a balloon on this side. I labeled this side 2, and the balloon is labeled number 2. And I labeled this side number 1, and the balloon is labeled number 1, although it's upside down because I am apparently a hack. I'm going to blow these balloons up and we'll see what happens. That look good? There we go. And this one. Yeah? All right. Okay, well, we'll cross our fingers. Aha! Balloon number 2 with the 2 facing you, balloon number 1 with the upside down 1 facing you. I'm going to open the valve and connect the 2 balloons. Your job right now is to guess what's going to happen. And I'm not going to give you the options, but when I open the valve, something's going to happen. Hopefully you have your guess. I'm going to open this valve. Doesn't matter which way I open it because it's just a straight through flow valve. That's balloon 1, that's balloon 2, and let's see how this goes. Now it's not a trick, the small balloon just filled the big balloon, and we're going to try it in reverse, and I know it's super tedious watching me inflate balloons, but I want to make sure you realize there's nothing shady going on. That look about right? Great. Let's get the other one. I'm going to have to inflate that one. All right, make sure that our balloons, there's number 2, you're just going to have to deal with it. There's number 1, you're just going to have to deal with it. And we're going to give it a try again. Now, once again, your job is to guess what's going to happen. And assuming I didn't screw this up, it's going to happen again, right? In the reverse direction this time, even though small is going to be filling large. All right. So once again, the small balloon filled the bigger balloon, and there's a reason for that, and we're going to take a look at the math in a little bit here. But for right now, I just want to try it again because it's very amusing to me, and I'm feeling a little dizzy. All right, that's balloon 2. That's balloon 1. 1 and 2. There we go. Oops, there's nothing fancy going on there. I'm not trying to trick you, I'm just incompetent. And again, the valve works, like there's no sleight of hand going on here. You don't even want to know how many balloons were injured in the filming of this. All right, and we got 2 and 1. So let's talk about the math here in a little bit. Here we are with balloon number 1 and balloon number 2 in a new location, same process taking place. I'm going to open the valve. We're expecting now balloon number 1 to fill balloon number 2. I drew a little L, you may have seen it in the video on the valve, just to show that it wasn't a one-way valve with an orientation changing. It would have been nice if I could have used different colored balloons, or if I had drawn the one upright, or many other things, but such is life. I had a lot of trouble getting these balloons to work, and when I tried different types and different brands, I was like a raccoon tearing the science department apart looking for decent balloons. This is what I got. At least it worked. We'll open the valve. Balloon number 1 fills balloon number 2 just as it did in my classroom. And now we're going to talk about why. The short answer is surface area and surface energy. Lower energy states are more favorable. That's it. And the bigger balloon, a single balloon with more particles, is favorable to a pair of balloons with fewer particles each. And in order to take a bigger look at that, we need to understand the idea of pressure and the pressure we're experiencing. So there's other videos I've done or will do on gas laws, and I want to start out like this is going to be my smaller balloon. We're going to pretend it's a sphere so people don't think it's a circle. And we need to look at air. There's air inside the balloon, and there's air outside the balloon. 80% nitrogen, 20% oxygen, 1% argon. Is more than 100%, but no one cares. Per the kinetic molecular theory, pressure is due to collisions with the container, right? All of these particles are moving. They have kinetic energy. They have temperature, right? They're not at 0 Kelvin, so they're moving. And statistically speaking, at some point, they're going to bump into something, be that each other or a container here. So that pressure is being caused by collisions with the container. Now, you don't see little ripples in the container as the particles hit it, because these are really tiny little particles, and there's bazillions of them hitting at any point in time. So it evens out, and you don't even notice the difference. Now, this would just crush this like a grape, except for the fact that there's a bunch of gas particles inside that are also colliding with the container walls, and they're pushing back with an equal force. In fact, that force in this particular case is pretty high. For this balloon right here, it's around 735 pounds of force, all right? Again, if that was a sphere. And there are some assumptions we're making to make our lives easier. Our balloons, perfect spheres, that's a lie. Linear elasticity or whatever, that's probably not the worst assumption. And other things like that. We're just assuming that the change in size of those balloons is due to pressure and surface area. All right, so let's take a quick note about pressure. Pressure is just a measure of force per unit area, okay? The units we'll be working with for this video are going to be pounds per square inch, or PSI. That is pounds per square inch, or lb per IN squared. And right now, at atmospheric pressure at sea level or whatever, we're experiencing a pressure of about 14.7 lb per IN squared. Now, what does that mean? I think it's kind of intuitive once you see it, which is for every square inch of surface area, there's 14.7 pounds of force, all right? So a square inch, approximately, that's experiencing 14.7 pounds of force right now due to air. Now, it's not pushing this piece of paper out of the way, because what's on the side of the other side of the piece of paper? More air. So this air here is pushing at 14.7, this air here is pushing at 14.7, and nothing happens, which kind of ties into gauge pressure versus absolute pressure that I'll talk about in a different video. Anyway, 14.7, which also becomes a huge deal in this other video, because you have a lot of surface area and the air is pushing on you really hard, and you're pushing out with an equal amount of force. All right, so let's take this into consideration. Looking at this, we know that surface area is going to be a big issue, because the more surface area you have, the more force is going to be felt. And by you, I mean spheres, and by spheres, I mean my balloons. So I have made some approximations of our balloons. That's my approximation of a valve there. I've got the big balloon that we started out with and the smaller balloon that we started out with. These are spheres, in case you can't tell. And then something else that we're going to see in a moment. Through the miracle of modern editing, I was able to add in this table that we can use to collect some of our geometric data and analyze what's happening as the small and the big balloon turn into a bigger balloon. We're going to use some standard geometric calculations based on radius, and we'll fill that information in right here for now. And then we'll calculate things like surface area, volume, and force on the surface. So let's start out by listing what our radii are. And those radii are going to be given in inches. Now, normally you just put the units in the edge of the table and carry them across, but for visual effect, I'm going to put them in each box as well. The big balloon that we have here has a radius of 4 inches, all right? The smaller balloon we have here has a radius of 2 inches, and those numbers there are going to be the basis for all of our calculations going down. The second thing of interest to us is the surface area. Surface area of a sphere is calculated using 4 pi r squared. So surface area as 4 pi r squared. And we can get our surface area here using our 4, and we end up with about 200 square inches. And sorry, I switched right from inches to double hash marks, but you'll live. 50 square inches over here. And we can see right now that while the radius has doubled, the surface area went up by a factor of 4, which is what you'd expect for this exponential relationship, right? And once we've taken care of our surface area, we now need to interpret how things are going to change when we combine the volumes, all right? So volume is our next item of interest. Our volumes are going to be in inches cubed. And to calculate that, we're going to say that V equals 4/3 pi r cubed, okay? And that's the volume of a sphere. And when we look at that, for a 4-inch sphere, we end up with around 268 cubic inches. And for a 2-inch radius sphere, we get around 33.5 cubic inches, all right? There's a minor omission here. I'll sneak it in. This will be in inches squared, and that was in inches. All right. So again, we can see a pretty significant change here, and that change is due to the fact that this is inches, inches squared, and inches cubed, so that change becomes more drastic. And then we're going to see the effect of that, at least this effect, when we look down here. All right, and all of these are going to be necessary for our comparison later. Now what we're worried about is the biggest factor we see, or at least the most quantifiable way we can spot the differences and why these balloons change, and that's what I'm just going to label as a surface force. The balloons have a surface area. Atmospheric pressure is a force per unit area, and so you can calculate the force over the entire area by multiplying. So I'm going to take that surface area times our pressure, right? And our surface area is going to be in inches squared, and we're going to multiply by pounds per square inch, and we're going to end up with pounds force. And I'm going to throw that little F in there to signify that. We've got the surface forces then based on this. 14.7 times 200 is 2940. And 50 times 14.7 ends around 735 pounds of force. And I don't think this is intuitive when you first look at it, but what we're saying is this balloon, or perhaps you could see it as this balloon if it'll focus, has about 2,500 pounds of force on it, right? Sorry, 2,900 pounds of force on it, which is about, you know, the weight of a small to medium-sized car. And if you were to just stack a car on this balloon, it would pop. In fact, if I were to stand on this thing, it would pop. The difference is, though, we've got these particles bombarding all sides equally in each direction, and we've got the particles inside pushing back out uniformly, and so that 3,000 pounds is distributed over the entire surface. And it turns out that there's enough surface area here for that to be a pretty reasonable number. Our smaller balloon, just 735 pounds of force. But overall, we've got about 3,700 pounds of force there. And I'm going to add that to this box right here, because that's going to be our combination box, our combined box. Data for our big balloon, data for our smaller balloon, and then when we combine them, what happens? Well, first of all, when we combine them, the radii don't add directly together. In fact, we're going to see far from it. So this, I'm just going to put an X through here, because without a little more math, we're not going to be able to predict that. But our surface area does add directly. This balloon has 200 square inches, this one has 50 square inches, so we end up with around 250 inches squared. Our volumes do add directly, and just for a simple approximation, we're just going to say that ends up around 300 inches cubed. All right? And then down here, since our surface areas add directly, our surface forces can add directly. And as I said a minute ago, that's going to be around 3,700 pounds of force for those two things combined. So this is, and I'll label it right here, our combined parameters for this balloon and this balloon right here. And so when we do actually take these balloons and combine them, what happens? The answer is our volumes have to stay the same. I have this much volume for a certain number of moles at a certain temperature with a certain pressure. And so then I have a set number of, or a set volume there for a certain number of moles at a temperature, at a pressure. And when I combine them, those volumes have to add directly. And so when these two balloons go together, those volumes go together. In fact, this 300 right here is going to carry over. So that number is the same between the two things because we have that much stuff, and that much stuff takes up that much space, period. Okay? Our surface area for this new balloon, we can't figure out immediately because we're going to need to know a radius. And the easiest way to get that radius, or at least for me, is to turn that 300 cubic inches back into a radius using the equation we had right there. So we're going to rearrange that and come up with our radius. Since we have 4/3 pi r cubed, we rearrange, we get the cube root of 3v over 4 pi. So let's write that out. Our radius is going to be the cube root of 3v over 4 pi. And since our v is 300, we end up here with a radius of around 4.16 inches. All right. Now that's important, and in fact, it's important enough that I made another cutout for that balloon right there. So that's 4.16 inches. In fact, I took the time with a compass to draw these circles, as I mentioned before, to scale. In fact, this is a 4.16 inch radius balloon. Well, balloon. And this is the 4-inch one. And notice this tiny little difference around the edge, right? It does not seem like it, just visually, that the amount of space within that much more of our sphere can hold all of that, but it does, okay? And again, it's that cubic relationship, that exponential relationship. So this little tiny space around the outside is big enough that shell can hold this much volume. And there's not a huge increase in radius, and correspondingly, we're not going to have a huge increase in surface area between that one and that one. So I will set this one over here. In fact, maybe I can just put it right there for a visual reference as we go. Okay? So once we know that the radius is 4.16 inches, we can do 4 pi and square that. We end up with about 217.5 square inches for the surface area compared to 250, so way less surface area. So we've got around 33 or 32 and a half square inches less. So our difference here is going to be about 33 and a half times 14.7. And we're going to end up about 500 lower, 3,200 pounds of force for our combined system, this one new balloon. In fact, this balloon right here. All right? I wasn't expecting that to happen. Anyway, so what we want to talk about is minimizing surface force, minimizing surface energy, and there's a pretty big difference here. Regardless of your knowledge of science, I think it's safe to say that philosophically, less force is more favorable, being surrounded by less force. And you can think of that as stress or whatever. In our balloon, obviously, we're talking about surface area and surface forces and surface energy and those things, but it's all proportional, right? And a related thing that I think is kind of interesting about surface area and minimizing surface area and how nature works is that the most efficient three-dimensional shape, at least in terms of surface area, is the sphere. And that's why you see so many, at least partial spheres in nature. For instance, something that forms on its own, water droplets, when those are undisturbed by air resistance, those form as perfect spheres because they allow you to have a minimal surface energy. Low energy is favorable. Low energy states are more probable, okay? So when raindrops form, actually, we can see this same scenario. When you look up in the sky, you see clouds. Those clouds are many, 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 many tiny droplets of moisture. And those droplets, as they are, have an unfathomable amount of surface area. So clouds have this massive, massive surface energy to deal with. Well, what can happen is exactly what we saw with the balloons, which is a whole bunch of these with much, much surface area can start to evaporate and condense. They coalesce as bigger drops that then eventually fall out of the sky. So just like with our balloons, where this and this turned into this, now we've got raindrops where a bunch of these turn into this, and then more of this turns into this, which eventually turns into this and falls out of the sky. So that's what we're really looking at in nature. And I guess in terms of our balloons and everything else, the key idea we want to remember is that we want to minimize surface area to end up in a lower energy state, which is more favorable.